This next work is presented by Joshua Gorniak from Boston College on behalf of his colleagues Yoon Kim, Donglei Wei, and Namwook Kim. And they're presenting VizAbility-Enhancing Chart Accessibility with LLM-based Conversational Interaction.
Thank you for the introduction. I'm Josh. I'm an undergraduate student at Boston College, and it's my pleasure to present to you VizAbility. So data visualizations leverage the high bandwidth of visual perception, as can be seen in this complicated map over here. And our research question was, how can we effectively present complex information from data visualizations to both blind and low vision users? Now, historically, screen readers have served as the predominant and most accessible alternative to site-based website navigation, of which NVDA, JAWS, and VoiceOver are the most commonly used. However, when applied to data visualization specifically, screen readers reduce them to brief descriptions and mere numbers, therefore undermining their inherent visual advantages. To circumvent this, numerous research projects have been made to generate keyboard navigable text representations of charts to be used alongside screen readers, one of which is Ollie, a project by MIT. However, navigating complex chart structures can become less intuitive and more cumbersome when restricted to keyboard inputs alone. Alternatively, there have also been pathways exploring more efficient, nonlinear probing of the chart's contents via question and answer systems, of which the most recent are DVQA and VoxLens. However, these are very limited in the question types they support. And furthermore, existing chart Q&A systems overlook the specific needs of BLV users who frame questions differently when compared to those with sight. We seek to tackle this by augmenting keyboard navigation together with conversational interaction, fusing these together to provide a more well-rounded experience for our blind and low vision users. And here comes VizAbility. So addressing previous concerns about the lack of representation of BLV users in datasets, we benchmark upon an existing dataset of real blind and low vision user questions spanning 4 chart types. These are the map as seen before, a line chart, a scatter plot, and a bar chart, all accompanying them with complex and intricate questions. Furthermore, to solely focus and isolate on our Q&A performance, which is our main contribution, we input underlying chart data as a Vega-Lite specification rather than a pixel image. And we assume that an off-the-shelf conversion between pixel images to data exists on the market. Now I'll show you a brief overview of our system. So we begin by selecting the chart type, and in this case, we use the pre-selected bar chart. Users can then explore the structure of the bar chart using the keyboard navigable chart text, and they navigate using their arrow keys. So in this example, the user navigates to positive temporal polarities, and they can access the individual data values as well associated with that field. The user can then supplement their knowledge of the chart itself by querying the conversational module. We begin by suggesting 4 pre-generated questions to sort of kickstart the exploration, and then the user can then ultimately input their own questions either through text or through voice. And in this case, to aid transparency, we also sort of give an explanation as to how we derive the answer, which in this case is analytical and sourced from the data itself. And then finally, integrating both of these components together, we have navigation questions, which enhances navigation of the keyboard navigable chart structure. So in this case, the user asks how they can navigate to the year 1853 from their current location, and our system returns the exact shortest path instructions to get to where the user needs to be. Now take a deeper dive into the architecture of our system. So since we're using a real data set of blind and low vision user questions, a lot of them tend to be vague or maybe lack some context that could decrease the accuracy of our large language model. So to do this, we then implement a proactive error prevention strategy. We inject context into our prompt by extracting a textual representation of the chart structure, as can be seen over here. And together with the question, we then feed it to the large language model, which in turn outputs a more refined version of the user query without sacrificing the original meaning of the user question. And you can see now we have both the subject and the context, thus improving our ultimate response accuracy. Furthermore, we also employ query classification with the aims of creating more well-defined tasks for our large language model. We utilize few-shot prompting to classify user queries into one of 4 categories, those being analytical queries, which rely on data, visual queries for visual encodings, contextual queries for background information that may be pertinent to the chart, and finally navigation queries, which is the example we saw from before. And this categorization is sourced from a previous study. However, we don't just populate the few shots with arbitrary examples. We instead use more closely aligned questions and classifications to improve accuracy. And we derive these closely aligned examples from a validation set of real blind user questions by extracting the 4 most aligned query types per query type using cosine similarity. So as an example, going back to our previously refined user question, we can see that analytical query examples return the highest level of matches, and accordingly, the system categorizes this question as an analytical question. Following classification, our system then diverts into 3 separate branches, one for addressing analytical and visual queries, the other for addressing contextual questions, and then the final branch for addressing navigation questions. And we'll focus and look into each of those 3. First up is the analytical and visual question pipeline, and I will demonstrate using this example. What do orange data points represent for the scatter plot? To bypass the token restrictions and to give our large language model the full context and the full picture, we utilize a CSV agent, which compiles our data and our visual encodings that we extract from the chart into one CSV file. This, along with the chart text, the current user position in the keyboard navigable structure, and the original refined question are then fed into our prompt. And our GPT-4 ultimately returns the correct answer, which in this case is that the orange data points represent countries in Asia. The next branch, as I've discussed, is contextual questions, and we developed this with the aim to provide contextual knowledge on demand for better chart comprehension. So contextual queries seek information beyond the chart, as is seen by this question. What is GDP per capita, and why is it important, pertaining to the same scatter plot from before? To disambiguate potential ambiguities of terms of multiple definitions, we once again use the chart text we extracted from before to feed context into our prompt. And when fed along with the original refined question, we get a very well thought out response that not only gives a definition of GDP, but also explains its significance by tying it to a country's economic health. Finally, for the third branch, which deals with navigation questions, our main point was to integrate keyboard navigation with conversational interaction for better orientation and wayfinding. This is especially important for large data sets where the keyboard navigable chart text can become extensive and expansive. So here we have an example. The user is currently positioned on 1 of 6, continent equals Europe for the scatter plot, and they ask how they should get to the x-axis. So we feed the user question along with the chart text and the user's current position, that being Europe, into our LLM prompt. And the goal of the prompt and GPT-4 is to then fetch both the starting and ending nodes. In the case of this question, where the starting node is not specified, we assume that is the user's active position. We then employ a breadth search algorithm to get the shortest path, and this is then relayed to the user, who has the autonomy to execute the instructions themselves. Following our system implementation, we then had a quantitative evaluation. So as mentioned before, we benchmarked on an existing data set of real blind user questions, which contained fields for the figure, the question, as well as metadata explaining the question types. We consolidated the metadata into our 3 classification types. And then since these are real questions, we accounted for them by introducing the new taxonomies of open-endedness and answerability, as some of these questions were vague or referred to elements not present in the data itself. Finally, we finished our manipulation of the data set by manually computing the response ground truths, focusing both on correctness and also verboseness for our responses. Now, since the original study did not include navigation questions, as this is our novel invention, we queried GPT-4 to generate 48 plausible navigation queries, 12 for each of our 4 chart types. We then performed an 80-20 stratified random sampling to split to yield our validation and test sets. The 20% was used in our classification pipeline for populating the prompt of relevant question examples, and the 80% is used in our quantitative evaluation as a test set. So we began by first classifying our question classification. We used the binary evaluation and using GPT-4 as the judge. GPT-4 returned either correct or incorrect, and we can see it's visualized over here in a nice graph showing the precision, recall, and F1 scores by question type. Overall, navigation questions and analytical questions had the highest rates of correct classification, with contextual questions lagging behind. We then did a manual human assessment of VizAbility's response quality, using a Likert scale of quality ranging from 5 being very good to 1 being very poor answers. And you can see we achieved an 82.50% accuracy rate, including good and very good responses. And here's a more granular view of this, using the parameters of chart type, question type, as well as our new taxonomy that we introduced, that being open-ended and answerable. And you can see that 76% of the poor responses were classified as not being answerable. And this deals with the fact that these are real questions that could sometimes not pertain to the data set at all. And if we simply take these questions out, our system accuracy increases to a whopping 91.3%. We then used GPT-4 to evaluate our system response quality using the same assessment criteria. And you can see that since these results are very comparable and closely aligned, this allows us to validate GPT-4 as a reliable judge and extrapolate its functionality and its judging capabilities to other models, that being GPT-4 Vision. So using the same assessment criteria and the same prompt with GPT-4 that we used from the previous assessment, we then used it on GPT-4 Vision, and we saw much poorer results when using the same benchmark data set of questions. Finally, we conducted a qualitative evaluation. This consisted of 6 one-on-one online sessions with real blind and low vision users of varying levels of experience of screen readers. And the study consisted of 3 parts. First was an introduction to the keyboard navigable chart interface, then an introduction to our question and answer module, and finally we integrated both using the navigation queries that I explained before. Here's a brief description of the 6 users. As you can see, it's a very diverse pool of ages, genders, as well as charts interacted with, screen readers used, and the expertise of interacting with these screen readers. As for some insights we gained from the study, and this also ties into our future work potential, participant 1 saw the system's potential in providing testing accommodations for GRE exams, noting its superiority over human proctors in translating visual graphs. Additionally, participant 6, who teaches NVDA screen readers to the BLV community, expressed interest in incorporating the system into his own lessons. This concludes the talk. Thank you so much. You can access the paper using the QR code, and here are some questions to motivate your questions to me. Thank you once again.
All right, if you have any questions, join us at the microphone, or we can bring one to you.
That's a really nice system, and like I want to ask, like, when we are using All right, great. So I'm Zach from University of Pennsylvania, and I want to ask, like, when people using data visualization, we usually want to strengthen like different aspects of the distribution of the certain data, and we are using different plots to like highlight different like distribution, but like I wonder whether we like convey this kind of information in the test, whether this model still has the ability to like highlight those kind of like differences.
Yeah, so you're asking about the ability to highlight distribution trends?
Right.
If I'm correct, yeah, great question. So yeah, visibility, so that kind of falls under our analytical query category, and visibility has demonstrated the ability to not only explain trends, but then also apply its knowledge, external knowledge, to then explain these trends and explain why they're happening in the data sets.